Hello friends, subscribers and new viewers of this channel, and welcome to Digital Logics and FPGA tutorials. In this tutorial, we explain the basics of RS flip-flops, which are also known as SR latches. Furthermore, we explain how to implement RS flip-flops in the Verilog programming language and FPGAs. We use the Vivado development environment to implement the flip-flops. We will explain two approaches for implementing flip-flops. In the first part of this tutorial, we explain the working principle of RS flip-flops, and we will derive a truth table, characteristic table, and a characteristic equation describing the behavior of RS flip-flops. And in the second part of this tutorial, we explain how to implement the flip-flop in Verilog. Here's the copyright notice. This video lesson, developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. This lesson and the provided material should not be used as lecture materials on online learning platforms and in university courses. This lesson and the provided material should not be used to train an AI algorithm or a large language model. Flip-flops and latches are the building blocks of digital electronic systems and components that are used in computers, cell phones, and other electronic equipment. Flip-flops and latches have two stable states that can store state information. Flip-flops and latches are designed to change the state by applying the external control inputs to their input ports. Outputs of flip-flops and latches are usually the stored state and the logical complement of the stored state. In this tutorial, we explain the basics of the RS flip-flops. An RS flip-flop is also known as an SR latch. In the sequel, we explain the basic configuration and the working principle of an SR latch. SR latches can be implemented by using NOR, that is not OR NAND, that is not AND gates. In this tutorial, we use NOR gates. Over here, you can see the NOR gate symbol, and over here, you can see the NOR gate truth table. Here is input 1, and here is input 2, and here is the output. The first column in the truth table is input 1, the second column is input 2, and the third column is output. We can see that the output of the NOR gate is 1 only when both input 1 and input 2 at the same time are equal to 0. Over here you can see the configuration and the working principle of the basic SR latch. We simply take two NOR gates. Here's the first NOR gate, and here's the second NOR gate. And then we establish the feedback. The output of the first NOR gate is connected to the input of the second NOR gate. Similarly, the output of the second NOR gate is connected to the input of the first NOR gate. That is, over here we have a feedback mechanism. The SR latch has two inputs. One input is the set input, and it's denoted by the capital letter S. You can see it over here. And another input is the reset input, which is denoted by the capital letter R, and it can be seen over here. On the other hand, the SR latch has two outputs. The first output is the normal output and denoted by the capital letter Q, and over here you can see the normal output, and we have the complement output denoted by the capital letter Q bar, and over here you can see Q bar. That is the second output. As written over here, the normal output is a logical complement of the output Q bar. That is, when the normal output Q is equal to 1, the other output should be equal to 0. And other way around, when Q bar is equal to 1, Q should be equal to 0. There are several approaches for mathematically analyzing and describing the behavior of the SR latch circuit. And over here you can see one of these approaches. In this approach, we are going to construct a truth table describing the behavior of our SR latch circuit. First of all, in the first column, we place the values of the set input. In the second column, we place the values of the reset input. In the third column, we write the normal output, and in the fourth column, we write the complement output. Let's start from the beginning. Let us assume that set is 1 and that reset is 0. That is, over here we have 1 and over here we have 0. Now, since set is 1, independently from this input over here, the output of the NOR gate 2 will be equal to 0. Then this 0 will be fed through this feedback loop and connected to the input of the first gate. Now over here we have 0 and reset is 0, and since this is the NOR gate, the output will be 1, and consequently the normal output is 1 and the complement output is 0. Here's the second scenario. This scenario comes immediately after someone pressed 1 and 0. Then over here set is set to 0 and reset remains at 0. However, previously Q is 1. So let's analyze. Since set is 0 and the previous value of Q is 1, the output over here will be 0. This 0 over here is fed through this feedback loop and connected back to the input of the first gate. Now here we have 0 and reset is 0, and this produces 1, and consequently the normal output will be 1 and the complement output will be 0. Next, let us assume that set is set to 0 and that reset is set to 1. Consequently, over here we have 0 and over here we have 1. Since reset is 1, independently from this input over here, the output of the first gate will be 0. Next, this 0 over here travels through this feedback loop and goes back to the input of the second gate. Since over here we have 0 for set and 0 for this feedback signal, we have 1 over here. And consequently, we see that the normal output is set to 0 and the complement output is set to 1. That is, the reset will set the normal output to 0. Next, we have the case where both set and reset are 0, and this happens after set is equal to 0, that is, and R is equal to 1. That is, it happens after this case over here. Now, let's analyze the circuit. Over here, set is 0. However, the previous value of Q was over here 0. So we have 0 over here and 0 over here. This produces 1 at this port over here. That is, the complement output stays 1. Then over here 1 goes to this input and reset is 0. So we have 1, or actually we have, yes, 1 and 0, and then we have as the output 0. And as the result we have this row over here. And let's analyze the final case. In the final case, someone can press set to be equal to 1 and someone can set R to be equal to 1. That is, both of these inputs are equal to 1. Let's see what happens now. In this case, we have that both Q and Q bar are equal to 0, and this case should be avoided. That is, when 1 is applied to both S and R, both Q and Q bar become 0. And this violates the postulate that Q and Q bar are complements of each other. Namely, it cannot happen that if Q is 1, Q bar is also 1. That is, in that case, the rule of Boolean algebra will not hold. Consequently, we should avoid setting 1 to both S and R at the same time. There is another issue when both Q and Q bar are zeros and when both S is equal to 1 and R is equal to 1. Let us assume that after S is equal to 1 and R is equal to 1, we try to set both S to 0 and R to 0. In practice, due to the stochastic delays, this cannot be done at the same time. Namely, we will have that either S or R might stay slightly longer at 1. And this might happen even at the nanosecond scale. If, for example, S is equal to 1 stays longer than R is equal to 1, then we will have a short time period when S is equal to 1 and R is equal to 0. This will produce Q is equal to 1 and Q bar is equal to 0. On the other hand, let us assume that R is equal to 1 stays longer compared to S is equal to 1. That is, there is a short time period when R is equal to 1 and S is equal to 0. If this happens, then we will have that Q is equal to 0 and Q bar is equal to 1. That is, due to the stochastic delays, the state becomes indeterminate and uncontrollable since we cannot accurately control and predict a stochastic delay and we don't know where our system will go. Maybe, for example, after we have 1, 1 and then something happens, there's a small delay, we might go to 1, 0 or 0, 1. And that's why we should avoid this case over here. This is very important to keep in mind. However, in practice, a better idea is to add a clock and to use the clock to control the transitions and the inputs reset and set. In its basic form, explained previously, and you can see this part over here, the RS circuit and the RS flip-flop is an isochronous circuit. We can modify the configuration and architecture of the RS flip-flop such that it responds to the input changes during a clock pulse. And over here you can see what happens. We can add two AND gates, here is the first one and the second gates, and an additional binary clock input denoted by CP. The input CP is a train of periodic pulses. The non-zero inputs can be propagated through two AND gates only when CP is equal to 1. That is, only when CP becomes to 1, reset or set can be propagated through these AND gates. This is mainly because the output of the AND gate is equal to 1 when both inputs are equal to 0. And clock enables us to control when we can actually change the inputs and outputs. And this is a very important technique that leads to better stability of the general circuit. Next, let's create a characteristic table for our flip-flop. Let's introduce the notation. Letter K denotes a discrete time instant controlled by the clock pulses. That is, K can go 0, 1, 2, 3, 4, 5, etc. That is, we can count and increase K at every rising edge of the clock pulse over here. Then, we denote the current state of our circuit by this notation, Q of K. Q of k is the state of the system at the discrete time instant k. Similarly, Q of k plus 1 is the state at the next time instant k plus 1. And the inputs will be used to transition from qk to qk plus 1. So let's start. When the current state is 0 and when the set and reset inputs are 0, obviously the next state will be 0. Then, when the current state is 0, set is 0 and reset is 1, we don't change the next state. That is, the next state stays 0. Then, when the current state is 0 and the set signal is set to 1, while the reset signal is 0, the next state will be 1, and over here we change the state. Next we have our critical state, that is when the current state is 0, and when the set is 1 and then reset is 1, we have the indeterminate state. And the reasons are explained previously. Then, when the current state is 1, set is 0 and reset is 0, nothing happens. The next state is simply 1. Then, when the current state is 1, set is 0 and reset is 1, we switch the next state. The next state becomes 0. Then, when the current state is 1, set is 1 and reset is 1, nothing should be changed. That is, the current state and the next state should be equal, and they should be equal to 1. And when the current state is 1, set is 1 and reset is 1, we have the indeterminate state that's actually controlled by the delays in the system, and it's very difficult to predict it. On the basis of this characteristic table, we can build a K-map, and finally we can derive the characteristic equation. It's given over here. That is, the state at the next time instant k plus 1 is equal to the input set, logical OR, complement of reset, logical AND, Q. And that's it. Over here, there is another condition, is that S and R is equal to 0. And that's it. These two equations mathematically describe our flip-flop. This condition is very important. This condition is saying that S and R at the same time shouldn't be equal to 1. If that's the case, then this equation is not satisfied. This equation is satisfied when S is 0 and R is 0. That's the first case. Then it's satisfied when S is 1 and R is 0. This is the second case. And the third case when S is 0 and R is 1. And the last case, S is 1 and R is equal to 1, doesn't satisfy this equation. Now, we can also derive the compressed characteristic table, and this characteristic table can help us to implement the flip-flop in Verilog and in our FPGA. So here's the compressed characteristic table. The first column is S, the second column is R, and the third column is the next state. We can see that when both S is 0 and R is 0, we have that nothing changes. That is, the next state is equal to the previous state. On the other hand, when S is 0 and reset is 1, we are transitioning to 1. That is, the next state is 0 independently of what the previous state was. Then, when set is 1 and reset is 0, we have that the next state is 1. And finally, here is our critical condition. That is our indeterminate condition. 1, 1 produces this X, which can either be 0 or 1. And over here you can see the symbol for our flip-flop. You can see over here we have the clock input, you have R and S, and you have the normal output and the complement output. And that's it. In the sequel, we explain two approaches for implementing the flip-flop in the Verilog programming language and in FPGAs. Okay, let's start with implementation. The first step is to open Vivado. So click on Start and search for Vivado. As you can see over here, in my case, I'm using Vivado 2024.1. However, you can also use any other version of Vivado. The Verilog code is the same. Let's create a new project. Let's click on Next. Let's keep these default settings, and let's keep over here default settings. And in this tutorial, it really doesn't matter the type of the board you're using. I'm going to use Nexus A7, however, you can also use any other board, or you don't need to even use a board. So I will search over here for Nexus A7-100, then I will click on Next, and I will click on Finish. Okay, now over here, wait for a while, and let's create our design sources. So click over here, click on this plus, and make sure that Add or Create Design Sources is selected. Click on Next, click on Create File, and over here, let's give the name to our file. I will call the file simply as flip-flop. And click on OK, click on Finish, OK, and Yes. And over here, you need to be patient. Then expand this folder Design Sources, double click on the file, and let's edit this file. First of all, let's erase these comments since we don't need them. So let's select the comments and let's erase them. As you can see over here, Vivado is very smart, and Vivado already gave the name to our module. The module name is flip-flop, and this name is the same as the name of the file. So let's keep this name as it is. First of all, we need to define the parameters of our module. The parameters are S, which will be the set input, R, which will be the reset input, then we have our clock, I will denote it by CP, then we have the normal output, and we have the complement. I will denote the complement by Q bar and the normal output by Q. Next, we need to declare the inputs and outputs. So we type input, and then we specify a list of inputs. They are S, R, and CP. And then over here, we need to specify the output. The outputs are Q and Q bar. Now, in our case, we need to declare that Q will be of the data type register. Consequently, I need to type reg Q. And let's analyze what we need to do. We need to implement our flip-flop. And the state change can only be possible on the positive edge of our clock. Consequently, I need to use the always statement. Then I need to type always at, and then over here I need to specify pos edge, which is a short name or the keyword for positive edge of our input CP. That is the positive edge of our clock. Let's start a block and let's close a block. So let's explain always statement. Always statement consists of this keyword always, then this add symbol, and inside we have the sensitivity list. In our case, the sensitivity list is simply the positive edge of CP. That is, this block over here that we will define in the SQL will be triggered on every positive edge of CP. So let's see what we need to implement. In this first example, I'm going to implement simply the last truth table. That is, I'm going to implement this. This is one approach for implementing the flip-flop, and in the next example, I will present the second approach. The second approach will be based on implementing this equation. So, over here, we need to implement this table. What's the easiest way to implement this table? You can simply define several if-else statements. However, this might be too cumbersome. There is a more elegant way, and let me explain that way. So let's go back over here, and we are going to use the case approach. This case approach is similar to the standard case approach or switch in C, C++, Java, MATLAB, etc. So let's type case and then let's use this concatenation operator, curly braces, and let's specify what we want to concatenate. We want to combine S and R. And over here, we need to specify what are the cases. First of all, let's look at the table. We can have 0, 0, 0, 1, 1, 0, and 1, 1. Let's start with 0, 0. 0, 0 in bit notation is denoted like this. 2, then the symbol over here, B standing for bytes, bits, sorry, this is bits, and then we have 0, 0. So this is 0, 0 for S and R. And you can see the power of this nice concatenation approach, since you can simply concatenate 2 bits, that is 2 inputs, and you can simply type this. This will be 0, 0. And then what we need to write, we need to say this. Let's see our truth table. The next state is equal to the previous state. So let's type it here. We type it like this. Over here, we need to use non-blocking assignment. That is, we need to use this operator here. You shouldn't use this. You should use this operator, and this is very important. So this is the first case. What's the second case? Well, let's see. The second case is 0, 1, and in this case, we should assign 0 to the next state. So let's type it here. 2, then we have 0, 1, and we need to type Q, that is the next state, will be simple single 0. That is, we write it like this. Next, let's analyze the third row. Third row is 1, 0, and we should assign 1. So let's implement. Over here, we need to type 1, 0, and then we need to assign to Q 1. We type 1 like this. And finally, we have the last case. This is the famous indeterminate state, and for a determinate state, we can simply type this. Then the Q will be simply 1 bit X, where this X is actually indeterminate. Okay, so this is the implementation. Now we change Q. However, over here, we also need to do several adjustments. Here it's not AND, here is AND case. This is very important to keep in mind. And then we need to end our begin statement over here. So keep in mind, once you open begin, you need to end. Once you start case, you need to end the case. And finally, we need to assign the value for Q bar. For that purpose, we simply type assign Q bar will be equal to not Q, and that's it. Simple as that. This implements our flip-flop. Let's analyze. Over here, we declare inputs and outputs. We need to declare Q to be a register data type. This is mainly because in this always statement, Q is on the left-hand side, and it has to be a register, and it has to memorize a state. This is very important. Here we are changing the state on the basis of the S and R values. We are ending the case, and here we are defining Q bar. That's it. Let's save this and let's proceed. Next, we need to simulate our flip-flop. For that purpose, we need to create a test bench file. So let's do that. Go to the simulation sources, do the right click, and click on Add Sources. Then make sure that you select Add or Create Simulation Sources, click on Next, and click on Create File. I will call the file simply as Test Bench, and click on OK. Then click on Finish, click OK, and click Yes. Now here you need to be patient. Next, expand this subfolder sim1 and find the test bench file. Double click and let's start with definition of our simulation. First of all, let's erase these comments. Next, we don't need the parentheses. Let's start with declarations. I need to declare equivalent variables, that is, equivalent inputs and outputs inside of my bench file that are equivalent to the inputs and outputs inside of my module. And for that purpose, I'm going to copy everything from here and I will paste it over here, just temporary. First of all, I will introduce the convention. If S is the original name, the name in the test bench file will be st. Similarly, for instead of R, I'm going to use RT. Instead of CP, I will use CPT. Instead of Q, I will use QT. And instead of Q bar, I'm going to use Q bar T, where T stands for test bench. Next, I need to declare the registers. In my case, the registers will be the inputs. Again, here is very important thing to keep in mind. In the test bench, the inputs should be defined, or better to say declared, as registers. So I will have ST, RT, CPT. Let me copy this part and let me add semicolon. QT and Q bar T should be declared as wires. That is a simple nets or signals. Next, I need to define my unit under test. To do that, I need to go back to the flip-flop. I need to copy the name of the module. The name of the module is flip-flop. Then I will call my unit under test simply UUT. And then over here, I need to add semicolon. Let me expand this. And I need to define the connections. Input S from my module will be connected to ST. And I perform this connection and establish the connection like this. I type dot, then I type input from my original module, and over here I'm connecting this input with ST. And I need to do the same thing with other inputs and outputs. So let's start with R. In the module I have R. However, in this test bench I have RT. Then let's do the same thing for the CP. In the module I have CP. And in my test bench I have CPT. Let's add comma and let's do the same thing for the outputs. Q should be connected to QT. And dot Q bar should be connected with Q bar T. And that's it. Let me now do this and let's continue. Next, I need to create a train of pulses. That is, my clock will behave as a train of pulses. I can do it by using the always statement and a single line. Namely, I can type always, then I can introduce a delay. This will be the period of my pulse, and I can simply type CPT is equal to not CPT. This statement will switch the value between 0 and 1, and the period will be 20 time units. The time units are defined at the beginning of the file. In my case, the time unit is 1 nanosecond. Consequently, the period of my clock will be 20 nanoseconds. So let's initialize and start our simulation. To do that, we need to type initial and then begin. And then we need to, first of all, and let's end. Don't forget to end here. This is very important. So initially, we need to set the clock. We are setting the clock value to be 0. Then I'm going to introduce a delay of 40 units or 40 nanoseconds, and then I'm going to sweep through this table over here and to test different cases. So let's do that. First of all, I need to have 1 0. Okay, so how to do that? Again, I can use the concatenation operator. I can type st dot or comma rt, and over here you need to be very careful what you're doing, since st and rt should actually be these st and rt, not s and r from our original module. That is, they're connected. Then you need to specify the value. The value should be 1 0. So I'm starting with set 1, reset 0. Then I will wait again for 40 nanoseconds. Then I will type a different value. I'm going to then put set to 0, reset to 0. Then again, I'm going to wait for 40 seconds. And then I'm going to reset by sending 0, 1. And then finally, I'm going to repeat this part. That is, I'm going to set the reset to 0, and that's it. Okay, so let's save this. Let's make that everything is okay. And let's run the simulation. To run the simulation, click here and click on Run Simulation and click Run Behavioral Simulation. And over here, be patient. It's going to take a while to run the simulation. And after some time, you will see this window over here that shows the time diagram of our simulation. Currently, it's not being zoomed out properly, so click here several times to zoom out, or you can press and hold Control and the middle mouse button to zoom out. Okay, so let's see what's happening. Let's zoom in a little bit here, and let's see. Okay, first of all, over here you can see set, reset, clock, Q, and Q bar. Here's how the clock behaves. It starts from 0, as we expected, then it switches to 1, then back to 0, 1, 0, 1, 0, 1, 0. Let's see the period of the clock. Over here, the period of the clock should be 20 nanoseconds, and if you go to the simulation, we can actually see that we have 20 nanoseconds. Now, let's see what happens initially. Click here to bring the slider and move the slider. Over here, we can see that initially clock is 0. This is as expected, since over here we set the clock to 0. However, we can see that set is undefined, that is its X, reset is undefined, QT is undefined, and Q bar is also not defined. So let's move forward, 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 and let's see what happens at 40. At 40, we are actually having the exact values for set and reset, and that's precisely what's happening after 40 nanoseconds. Okay, now set is 1, reset is 1, and let's see what happens. Set is 1, reset is 1, however, we can see that Q doesn't change. Interesting. Why is that? Well, this is because by looking at our module over here, we can only change the values on the positive edge of CP. However, over here we switched before the next positive edge of our clock, and consequently the values will not immediately change for Q and Q bar. They will actually change on the next positive edge of the clock. That is, they will change over here. And now you can see that Q and Q bar are actually nicely defined. And if we switched to 1, that is, the state becomes 1. We go further, we further. Now over here, after 40 seconds, we are executing this. We are setting set to 0 while the reset was 0. And that's what's happening over here. Nothing changes with the state. And this is the correct behavior. Now over here, after 40 nanoseconds, we reset. And if there is no clock, you will see that immediately the output value, Q, will go to 0. However, it doesn't happen immediately. This is because we need to wait until the clock, and when the positive edge of the clock arrives, that is when the rising edge is detected, then the switching occurs, and then you see that Q is set to 0 and Q bar is set to 1. Then finally over here we set both the set and reset to 0. However, nothing changes with the output, and the output stays the same. And that's it. And that's precisely what you have over here. Here it is. This means that we have correctly implemented our flip-flop. Next, we present the second approach for implementing the flip-flop. This approach is based on directly implementing this equation. So let's start. Go back to Vivado, click on File, then click on New Project. So click on Projects, New, then click on Next, Next, Next. Over here, click on Boards, find the board you like. I'm going to use this board over here, click on Next, and click on Finish. And over here, I'm going to close the previous project, and let's start. The first step, as always, is to create our module. So click on Design Sources, then click over here, make sure that Add or Create Design Sources is selected, then click on Next, click here on Create File, and call the file flip-flop. And click OK, click on Finish, and OK. And yes. OK. Let's now wait for a while, then expand this folder, double click on the file. Let's erase the comments. And again, we need to specify the parameters of our module. We have S, R, CP, then we have Q, and we have Q bar. Okay, then we need to declare the inputs and outputs. We have input, which are S, R, and CP. Then we have outputs, so we type output, Q, and Q bar. Okay, these are the outputs. Next, we need to declare Q to be a register data type, so we need to type register Q. And then over here again, we will change the state on the positive edge of our clock. So we need to use the always statement, then we need to specify at, and we need to specify positive edge of our clock. We do it like this. Let's start begin, and let's end everything with end. Okay, we need to implement these two equations. So let's do it. First of all, we will check for this indeterminate condition. If this is the case, we can actually implement this equation. Otherwise, we're going to specify that the next state will not be determinate. That is, it will be indeterminate. So let's type it over here. To do that, we need to use the if statement. So we need to type if, then let's open parentheses, then another parenthesis, and let's type S and A, S and R's actually, is logically equal to 0. That is, we are testing if S and R is 0. If that's the case, then we begin if and we end if. Inside of this if, we simply need to implement our equation. So let's look again into equation. Next state is actually S logical AND, not R, or actually sorry, S logical OR, not R logical AND Q. So let's type that. So we have Q, then we use non-blocking statement, S or you type like this, you use these vertical bars, then parentheses are opened. Inside we will have not R, right, and Q, and then let's add a semicolon, and that's it. Okay, otherwise, let's put here else, and let's do begin and end. Begin, and let's end here the else statement. And over here we simply need to specify that Q is not defined. So let's type this. Again, let's use non-blocking statement. We're simply setting to be X value. And that's it. Simple as that. And then at the end, let's make sure that everything is open and closed. We have if opened. And over here, right, if begin, and we need to verify this because whenever you type if, you need to type begin and then else, begin and end. Outside of this always block, we need to specify the value of Q bar. Consequently, we need to type a sign Q bar is equal to not Q, and that's it. Let's save this and let's create our simulation. To create a simulation, let's again go here, click on simulation, do the right click, click on add sources, make sure that add or create simulation sources is selected, click on next, click on create file. I will call the file as test bench, click on OK, click on finish, and click on OK, and yes. And now let's open the file, expand simulation over here, double click, and over here let's use the previous simulation file. Consequently, I will simply copy and paste the content of the previous simulation file since the simulation is identical. So I will copy it here, I will paste it here, and let's again go and analyze the simulation file. Over here we specify the time scale, we define our module test bench, we specify that these ST, RT, and CPT inputs are registers, QT and Q bar T are wires. Over here we define our unit under test and we connect the variables used in test bench with the inputs and outputs inside of our flip-flop module. Then what do we do over here? We define a clock with a period 20 nanoseconds, and inside over here we perform simulation. We initially set the clock to 0, then after 40 nanoseconds we switch to 1, 0 for the set and reset, then we wait 40 nanoseconds, then we switch set and reset to 0, 0, then again 40 nanoseconds, we switch the set and reset to 0, 1, then again 40 nanoseconds, and we switch set and reset to 0, 0. And that's it. Simple as that. Let's save this test bench file and let's run the simulation. Go over here, then click on simulation, expand it, and click on run simulation, then run behavioral simulation, and here it is. And then let's be patient, expand the simulation window, make sure that it's normally expanded, and then let's zoom out and let's analyze what's happening. The simulation should be the same as the previous simulation. So let's see what's happening. First of all, we can see that the clock is properly defined. And let's see where do we switch. Over here, after 40 nanoseconds, we go to 1, 0. However, the output and the complement output will not be switched. This is because they can only be switched when the clock is going from 0 to 1, that is on the positive edge of the clock, and we can see over here that they are properly switched. Then again we switch set to 0, however the outputs do not change, and this is the expected behavior. Then we go further, then let's see what happens over here. The clock switches, then over here we go set 0, reset 0, and we can see that nothing changed with the output. This is because the output the state can only be changed when the clock changes, and over here we can see that the state goes to 0, and this is expected behavior. Then we go further, then set is 0, reset is 0, and from now on nothing changes. And that's it. From here we can see that the simulation is properly executed and we have properly implemented our flip-flop circuit. Okay, that's all for today and thanks for watching.